Okay. So thank you very much for the introduction, Lars, and thanks for the organizers for inviting me here. It's a great honor, and also thanks for the jury for selecting our paper. So it's a paper which again is joint with Sergiu, Klainerman, and Igor, Rodnianski. So I'm assuming that not everybody is familiar with GR, so I'm going to start with recalling what are Einstein equations, and here in fact I will focus on the Einstein equations in the vacuum, and we'll see that this is in fact an evolution problem. Okay, so here my main object is the Lorentzian manifold. So the dimension of my manifold M is 4, 1 for time, 3 for space. So it's a correct physical dimension. And the Lorentzian metric G, here my convention will be that the signature is minus, plus, plus, plus. And of course the simplest example of such Lorentzian manifolds is the Minkowski spacetime, which is given here, which is the framework of special relativity. So M is R1 plus 3, and the Minkowski metric here, I write it down in Cartesian coordinates. So minus dt square plus dx1 square plus dx2 square plus dx3 square. Okay, so the Einstein's equation, Einstein's theory of gravity, which is general relativity, interprets gravity as the curvature of the spacetime. Okay, so you need an object that will measure the curvature of the spacetime, and this will be the so whenever I say spacetime, sorry, I mean the Lorentzian manifold. Okay, so this object is the Riemann curvature tensor. It's a 4 tensor, and if you don't know what is the Riemann curvature tensor, it's not too important. Just imagine that this is an object that tells you the distance from the Minkowski space, simply because if the curvature is locally 0, then you are locally isometric to Minkowski. So it's really an object that tells you everything you need to know about the curvature, and in particular tells you somehow how far you are from the flat case, which is the Minkowski spacetime. Okay, now this curvature tensor, which is a 4 tensor, you can take a trace, in which case you get a 2 tensor, which is symmetric and called the Ricci tensor. And that tensor only contains partial information on the curvature. And with this object, which is the Ricci tensor, I can now state the Einstein equations in the vacuum, which are the, well, apart from one slide, the only equations I will mention. And they correspond to any Lorentzian manifold with a vanishing Ricci tensor. Okay? Okay, so that's the equations I want to look at. In this form, the only thing you can say is that this is a PDE. In other words, if you look in coordinates, the Ricci tensor takes the form of 0 first and second order derivatives of the metric, but it's not clear what the nature of this equation is. So let me provide you a simpler form of these equations in a particular setting. So here I will use what is called so-called general covariance, which is a very important principle raised by Einstein, which is the fact that, in fact, the laws of physics should not depend on the particular coordinate system. There is no preferred coordinate system. And for us, for practical purposes, it means that we have the freedom to pick any coordinate system we want to write down these equations. So here, for you, let me pick a very simple one called wave coordinates, which is the analog of harmonic coordinates in Riemannian geometry. And if you take these coordinates, let me not say how you define them. It's not too important. What is important is that, in fact, in these coordinates, this is the kind of equations you would see. In other words, the Ricci equal to 0 is written in the following form of a coupled system of nonlinear wave equations in the coefficients of the metric G alpha beta. So G is a 4-dimensional metric. It's a symmetric 2 tensor in dimension 4. So it has 10 degrees of freedom. So this is a coupled system of 10 nonlinear wave equations where the coupling is through this right-hand side here, which I'm not going to write down, and which is an expression involving the metric and first-order derivatives of the metric. Okay? And then I want to say that this equation is in fact what is called quasi-linear. It's a quasi-linear system of wave equations, simply because even the term on the left-hand side, is nonlinear. In other words, here the term on the left-hand side contains the second-order derivatives, and here you have this D'Alembert, but it's not the D'Alembert in the flat space. It's not the D'Alembert in Minkowski. It's the D'Alembert which depends on the metric, which is the unknown of the problem itself. Okay, so that means that here you even have nonlinear second-order derivative expressions. So this is the so-called quasi-linear case, and the reason I'm introducing this terminology is because I will come back to it later. Okay, so I want to mention that these are not at all the coordinates that are used in the result I'm going to present. It's just for the purpose of writing the Einstein equations in a simple way, in a simple form. Okay, but certainly under this form, we will recognize that given that you have a coupled system of wave equations, you certainly expect that this is an evolution problem of hyperbolic type, and therefore you need to set up initial data, initial conditions, or Cauchy data. Okay, so let me tell you what are the Cauchy data for this problem. So since you have wave equations, of course you expect to have to prescribe the metric at time 0 and time derivative of the metric at time 0, but let me actually give you the geometric formulation for this problem, because you always want to work invariantly. So the invariant way or geometric way to state the problem is to, for the Cauchy data, is to ask for a triplet sigma naught G naught K, where sigma naught is a 3 manifold, and it corresponds to the time slice t is equal to 0 in these coordinates. G naught is a Riemannian metric on sigma naught, and it is in fact the metric induced by the space-time metric on sigma naught, which you can think of as being G at time 0, the space-time metric G at time 0, and finally K is a symmetric to tensor, and it corresponds to the second fundamental form of the embedding of sigma 0 in the space-time M, in the Lorentzian manifold M. And of course, you can think of it as just being the first or the time derivative of the metric at time 0. Okay, so these are the Cauchy data. And now I can start talking about the evolution problem. In other words, the question of local existence, uniqueness, and maximal solutions. Okay, so this is a foundational result due to Ivan Choquebrua from 1952 and later Choquebrua-Garrosh in 1969, which says that if you start with sufficiently smooth and suitable, and let me not say what I mean by suitable, initial data, then Einstein vacuum equations are locally well posed, and furthermore, there exists a unique maximal solution. Okay, so here the statement of existence and uniqueness is due to Choquebrua. The statement of maximality of the solutions is due to Choquebrua-Garrosh. It's actually not an obvious statement to obtain in view of the general covariance of the equations. It's not so easy to compare different spacetimes and say that one is maximal. Okay, and now the main question I want to ask, and in fact it's actually closely related to the previous talk, I want to ask whether for this evolution problem, for these maximal solutions, whether they exist for all times, whether they are global, or whether singularity formed during evolution. And in fact, I'm immediately going to present an example where the answer is yes, there are singularities that can form. So I'm going to focus on the second equation, equation of the Einstein vacuum equations chronologically, the Schwarzschild solution, which was found by Schwarzschild in 1916. Sorry, maybe let me go back to the previous slide, and let me just say that obviously Minkowski is flat, and therefore it's Ricci flat. So Minkowski is certainly the simplest solution of Einstein vacuum equations. And here, let me describe the second solution which was found chronologically, which is the Schwarzschild solution. And of course, what I want to mention is that it contains a singularity. So it's a one parameter, in fact, it's not one solution, but a one parameter family of static and spherically symmetric spacetimes, which depend on a mass parameter M, which is strictly positive. And here I'm writing down the form of the metric in so-called spherical T, R, theta, phi coordinates of R4. And I just want to focus here, the form of the metric is not too important. I just want to focus on the metric coefficient in front of the R square, the one in red here. And this term is obviously singular both at R is equal to 0 and R is equal to 2m. Okay, so in general relativity, due to the principle of general covariance, so the fact that no system of coordinates is preferred, you want to distinguish between a true singularity, one which would be true in any coordinate system, and a coordinate singularity, one which has to do with a bad choice of coordinates. Okay, so it turns out that the singularity at R is equal to 0 is in fact a true singularity. Okay, on the other, in other words, in any coordinate system, you will see this singularity. On the other hand, the one that R is equal to 2m is in fact a coordinate singularity. It's a fact that I chose a bad coordinate system here to write the Schwarzschild solution. And in fact, you can find a new coordinate system in which you can make this singularity disappear. Nevertheless, this hypersurface is very important because it corresponds to the event horizon of the black hole region, which is in the region R strictly less than 2m. Okay, so here, I'm not going to define specifically what is a black hole. Here, it's not too important, but it's just to say that this is in the event horizon in the sense of this is the region that is not accessible by observation for outside observers, and we think of ourselves, of course, as being outside of the black hole. Okay, so if we think of ourselves as being outside of the black hole, this is the region we can see, and the event horizon is the boundary of this region that is not accessible. Okay, so to summarize, there is a true singularity, and it lies inside the black hole region in the case of the Schwarzschild spacetime. And maybe let me add one last comment. Again, these coordinates are not very suitable, at least once you enter the black hole. And in particular, the singularity r is equal to 0, you might think of it as being an eternal singularity, but it's not at all the case. The coordinate r here, you should think of it rather as a time coordinate, and you should think that the singularity r is equal to 0 is in fact towards the future. In other words, I can set up a well-defined initial value problem for one of the slices of Schwarzschild in which it will look smooth, and in the infinite time, it will form a singularity at r is equal to 0, which will lie in the future. So this is really an example of formation of singularities. Okay, so then, of course, people wondered whether this Schwarzschild singularity should be seen as a problem from the point of view of the Einstein's theory of gravity. Does it mean that the laws of general relativity break down? And the first answer was to dismiss this solution. I mean, dismiss the fact that it has a singularity, as people thought that this was due to symmetries. It was due to the fact that Schwarzschild has lots of symmetries. It's both strictly symmetric and static. And in fact, it was realized, I'm going backward. It was realized in the remarkable work of Penrose that in fact this is not at all the case. It has nothing to do, the Schwarzschild singularity is something of a much more general phenomenon. It has nothing to do with symmetries. It's something much more general, and that's the celebrated Penrose singularity theorem from 1965, for which he recently was awarded the Nobel Prize. And it states the following. So it gives you 3 necessary conditions to obtain a spacetime with singularities. And as you will see, these conditions are very general, so they have absolutely nothing to do with symmetries. Okay, so here I should be a bit more precise. This is not, Penrose doesn't prove that the singularity forms. What he shows is that the spacetime, under these 3 conditions, which I'm going to state, the spacetime cannot be future geodesically complete, null geodesically complete. In other words, some null geodesics cannot exist forever, which is the sign that something goes bad, but it doesn't really tell you how bad it is. It doesn't really tell you if the curvature blows up, if the Lorentzian character breaks down. I mean, it's not clear what goes wrong, but certainly something goes wrong. Okay, so let me state what are these 3 conditions. So the first is that the Ricci tensor, if contracted twice with the same null vector, is positive for any null vector fields. The second condition is that M contains a non-compact Cauchy hypersurface. So in other words, your slice T is equal to 0 extends to infinity. It's not compact. And the third condition, and that's the main one, is the fact that M should contain a closed trap surface S. Okay, so maybe let me briefly explain what the trap surface is. So let me recall what is the case of Minkowski. So if I were in Minkowski and I have a 2 surface, there are always 2 light cones that emanate from these 2 surfaces. There is one outgoing one and one ingoing one. So let me try to do a proper picture. Okay, and what you can see in the Minkowski situation is that the ingoing cone shrinks. In other words, if you look at the area of the spheres generating a null cone, the area of the spheres of the ingoing null cone tend to shrink, but the areas of the outgoing cone tend to expand. Okay, and that's the situation in the flat case for Minkowski. Now here, this is a very different situation. The case of a trap surface is the case where the ingoing cone still shrinks, but the outgoing cone also shrinks. Okay, so this is the kind of what this picture signals. Here you have the ingoing cone that shrinks. That's the case of the Minkowski space already. But here you are in a situation where the outgoing cone also shrinks. Okay, so this is measured by this quantity here, trace chi and trace chi bar, which are in fact the mean curvatures of, in other words, chi and chi bar, the null circumferential form of your surface as embedded in your space-time. There are 2 because the surface is codimension 2, and these mean curvatures, also called expansions, usually are such that you have a negative sign, and this is what it means to shrink. In fact, so both mean curvatures are strictly negative, while in Minkowski one would be positive and one would be negative. Okay, so that means, and here I should point out that you can have a trap surface in a perfectly smooth spacetime. You can think of, for instance, let's think that your initial slice contains this surface. It could be perfectly smooth and yet have a trap surface. And what this theorem tells you is then that this perfectly smooth initial data will lead to a singularity in the future, at least in some weak way of, in the sense of geodesic incompleteness. And you can see also that, this is a sign condition. So, once you have one trap surface, you can have many. So this is really, this is a way to cook up many, many examples of spacetimes with singularities in the future. Okay, so let me summarize. So far we have seen that these maximal solutions of even Schrecke-Brouwer and Schrecke-Brouwer-Garrosh, they can lead to many singularities in view of the Penrose singularity theorem. And let me ask again the question, should be, now we are forced to ask again the question, are these singularities undesirable from the point of view of Einstein's theory of relativity? And the answer of Penrose, who came a few years later, was to say, well, no, as long as they are hidden by a black hole. In other words, as long as they are not naked singularities. Okay, so here a naked singularity is a singularity that is visible to outside observers. In other words, we think of ourselves as outside of, let's say we are near infinity, and we get signals from spacetime, and what we don't want to see is a singularity outside of black hole, because then it will emit signals that we could actually see, and that would be considered bad. What is okay is if they are hidden by a black hole, because then of course we will never see them, and somehow we can forget about them, and that's hence the name censorship. The singularity is censored by the black hole. Okay, so let me maybe state this celebrated conjecture of Penrose a bit more specifically. So it's singularities of Einstein vacuum equations are generically hidden inside a black hole. And here there is the work generic to say that, well, you still expect that naked singularities coexist, you just want them to be non-generic. Okay, so here, so this is the so-called weak cosmic censorship conjecture, and if you want, maybe I can make a connection with the previous talk where we have seen the global existence conjecture for Navier-Stokes, which is one of the Millennium Prize. This is the exact analog for Einstein equations. You should understand this conjecture as being a global existence conjecture for the Einstein vacuum equations, which are also supercritical nonlinear equations. So this is a global existence conjecture in the sense global existence outside of black holes, at least for generic data. Okay, so let me maybe give a slightly more precise statement, even though it's still rough. So generic asymptotically flat initial data. For generic asymptotically flat initial data, you expect, according to this conjecture, that the maximal Cauchy development of the corresponding solutions to Einstein vacuum equations have a complete null infinity. And here I have highlighted the word generic, because that's the one I want to focus on. Genericity, this raises the question, in which norm should you measure genericity? You want to say that if there is a naked singularity, it can always perturb a little bit and show a new spacetime for which the singularity now is not naked anymore, it's hidden by a black hole. And that really raises the question, given that you are infinite dimension and norms, as we know, are not equivalent, that raises the question on how to measure genericity. Okay, so maybe to go to something more tractable, let me give you one example where this conjecture has been actually solved. So I should say that in general, it's a completely open problem, probably I would say at least as hard as the Navier-Stokes Millennium problem. Okay, but in the spherical symmetry, there is a remarkable proof and very influential by Demetrios Christodoulou from 1999, which settles the case of spherical symmetry. In fact, I should say that 99 is the latest work. It's a series of 5 works that range from 94 to 99. And the result of Christodoulou states that weak cosmic censorship holds true generically for the Einstein equations coupled to a scalar field in spherical symmetry. So here you can see that this is not about the Einstein vacuum equations, simply because the Einstein equations in the vacuum in spherical symmetry are non-dynamical. The only possible solutions in that case are the Schwarzschild solutions. So to reintroduce a dynamical degree of freedom, you need to couple the Einstein equations to a matter field. And here, Christodoulou chooses one of the simplest one, and also very relevant, which is the coupling to a scalar field. Okay, so maybe let me before discussing it further, let me just give you a picture, explain you the proof in one picture. Okay, so first of all, you start with a singularity. So let's say that I have a space-time. So this would be my singularity, right? So this is my singularity in the future of my initial data. Singularity. Okay, so I start with a singularity in the future, and I want to draw the backward light cone from that singularity. So that's my backward light cone. Okay, so naively, you might think that you want to perturb. So now I need to perturb and show that I will form a black hole, and it will hide the singularity. Okay, so naively, you might think that you have to change the path of the singularity, and so that you can remove the singularity. You can show that under small perturbations, I will remove the singularity. But this is not at all what the conjecture says. The conjecture doesn't tell you that the singularity will disappear. It tells you that it will be hidden by a black hole. So one of the great insights of Christodoulou was to say, well, I don't have to change the past. I will let this singularity where it is, and I will just change what is outside, immediately outside of the backward null cone from the singularity. So let me say that I'm setting initial data here, and I'm going to here perturb a little bit the initial data. So here, this picture is just there to say that I'm adding a small, and in fact arbitrary small, if I want to put genericity. Here I'm putting an arbitrary small perturbation. So arbitrarily small perturbation. Okay, and then of course the goal is to show, so the idea is that part of the perturbation at least will propagate along the backward null cone. And the idea, heuristically the idea of the proof of Christodoulou is that there is a mechanism, even though it's arbitrarily small at the beginning, there is a mechanism there is an amplification mechanism. And this amplification mechanism is a kind of, in fact, it's a blue shift effect. So there is a blue shift effect which makes this perturbation grow. And at some point, it becomes large enough. You can measure that it's large enough so that a trap surface forms before the singularity. So if you want, a black hole forms, but let me more locally. A black hole, I have to follow the entire space-time. Here, locally, my criterion to say that the singularity will be hidden is there is a trap surface forming around it. So let's say an S that forms before the singularity, and then which will hide the singularity from the outside observer. Okay, so this is really the idea of the proof of Christodoulou. And here, I should highlight that there are two main ingredients in this proof. One is a very rough local existence result. So and I will comment on this, but this has to do with the issue of genericity and how you measure it. And the second ingredient is, of course, in view of what I explained, a sharp criterion for the formation of trap surfaces. Okay, and so let me now explain why you need a very rough, why you need a very rough local existence result. In other words, why do I need in this proof? Why does Christodoulou needs crucially to make sense of very low regularity solutions? And this is the following explanation. So if you want to obtain a trap surface using this sharp criterion, you need to perturb the initial data. It turns out that you need to perturb the initial data with a jump along the backward null cone. Okay, simply because somehow you need arbitrary small perturbations, and to make something non-trivial, even if it's arbitrarily small, in fact it produces data with a jump along the backward null cone. Yeah. Yeah, exactly. Yeah, because here the dynamical degrees of freedom is scalar field. So you prescribe the scalar field, and it has a jump along the. In fact, I think it's a transversal derivative that has a relative to the cone that has a jump. Yeah.
So it's a singularity that tries to help the other one.
Yeah, it's a mild. As we see, it's a mild thing. It's not really. Yeah, sure, it is a singularity, but you can still make sense of the equations. It's. Yeah, sure, you could say it's a singularity that propagates. Yeah, if you want, you can see it that way. But it's still, you can make sense of the solutions, and you can show that they exist locally. So as long as you can make sense of the solution, I wouldn't really call it a singularity. But certainly, it's not a smooth perturbation. That's the
problem is that has
does it have infinite energies? I don't think so, no? Yeah, he works in the BV space. Yeah, of the transversal derivative of the.
discontinuous first derivative of argument. It's a discontinuity of the field.
Yeah, but I think it's not.
No, it's not a delta. It's a jump, right? It would be a delta for second order derivative of the field.
The first derivative
has just a jump, so it's like a heavy side, and second order derivative So second order derivative would have a delta. So I don't think. Yeah, the field is continuous. Okay, but in any case, given that, of course, that means that for this small perturbation, which is irregular, it has a jump, so you want to still make sense of the solution, so that still means that your whatever local existence result you infer, you need to make sense that of the solution in this. If you want to, you need to make sense of the solution in the space-time region, which would be roughly like this, so that you can show, you can control things and show that the Trapp surface forms. So this is why you want to make sense of very rough solutions. Maybe let me give you another heuristic argument why it's very good to consider rough solutions. The second argument is that somehow you want to perturb by arbitrary small perturbations. So you want to measure something as being arbitrarily small, but yet it should be large enough to produce a Trapp surface. So it shouldn't be too small either. Of course, that also indicates that you should look for very rough norms, because a very rough norm would allow you to see something as being a small perturbation, even though if you measure it in a smooth norm, it could be very large. So that's another indication that rough solutions are important. Okay, so this result of Chrysoulou was very influential, and what people tried to do since, in fact, is to extend, in fact, both types of arguments in the absence of symmetry. Okay, so I should say again that the conjecture is wide open at the moment, but the idea would be to extend both arguments. So there are many results on Trapp surface formation, but I'm not going to talk about those. What I want to talk about is this other important step, which is making sense of very rough solutions. And here, let me mention that there is an important distinction with the work of Chrysoulou. The work of Chrysoulou is in 1+1, it's spherical symmetry, and it's well known that there is a main distinction between hyperlic problems in dimension 1+1 and higher dimensions. And the main distinction is that in 1+1, precisely as last mentioned, you can work in the BV space, in other words, an infinity base space if you want, while if you work in higher dimensions, you have to work on L2 base spaces. So you have really to look at totally different spaces. And furthermore, in 1+1, one thing which is very important in the work of Chrysoulou is that any Lorentzian metric in 1+1 is conformal to the Minkowski space, which is, of course, absolutely not true in higher dimensions. Okay, so this is the paper presenting that has the awards. Again, it's joint work with Sergiu, Klainerman, and Igor Rodnianski. It's from 2015, and it's called the bounded L2 theorem because it solves, in fact, the bounded L2 conjecture, which was presented by Klainerman in 2000 in an essay on PDEs at the turn of the millennium. Okay, so let me provide the statement. So again, recall that the initial data set consists of sigma naught, a 3-manifold G naught, a Rodnian metric, and K symmetric to tensor. And then in terms of regularity, you want to assume that the curvature tensor of G0 is in L2 of sigma naught, and you want that the covariant derivative of K is in L2 of sigma naught. And then under these low regularity conditions, you want to prove that, we prove that Einstein vacuum equations are well posed. Okay, so so the first part of this talk was a motivation for these low regularity results, and now let me give you some more context to compare these results with the literature. Let me first recast again the equations in the more general context of quasi-linear wave equations. We have seen earlier that you can write down the Einstein equations as a system of quasi-linear wave equations. And as a system of quasi-linear wave equations, this is in fact the first result to go below H2 plus epsilon. H2 plus epsilon is the famous result of Smith and Tataru from 2005, and it is optimal in general. So the only reason you can go below is by showing that the Einstein equations are better than any generic quasi-linear wave equations, and I'm going to talk about this, but you have to fundamentally use the full nonlinear structure of the equations, and in particular, certain cancellations known as the null structure in the nonlinearity of the Einstein equations. So here, just to compare, here the curvature tensor is in L2, so it's at the level of 2 derivative of the metric in L2. So this means regularity at the level of the Sobolev space H2, while this result is in H2 plus epsilon. Okay, so it's going down by an epsilon from the Smith-Tataru result, but again, because the Smith-Tataru is optimal in general, you have to go to dig much more in the nonlinear structure. Okay, let me also comment on the fact that the assumptions here are invariant. This is always important when you work with Einstein equations. These assumptions do not depend on coordinates because the curvature tensor, the L2 space, and the covariant derivative of K are all invariant objects, which means that you can use this theorem in any in your favorite coordinate system. You don't have to stick to coordinates tied to these results. This is of course not the case of the space H2 plus epsilon, which will require to fix a coordinate system from the start. Okay, and this third point here is important in connection to the result of Christodoulou. In fact, what Christodoulou does is he uses his BV well-possessed result both as a well-possessed result, but as importantly also as a breakdown criterion. In other words, a criterion on knowing whether a quantity becomes singular or not. Okay, so his criterion. So here it's also a breakdown criterion. In other words, this result tells you that as long as curvature stays in L2, then if you stay smooth and your curvature stays in L2, then you remain smooth. So there is a propagation of regularity results behind this statement, which means that curvature in L2 is a fundamental quantity controlling singularity formation. And finally, let me discuss criticality. I claim that there is some criticality in this problem, but not in the sense of the previous talk. So here, there is also a scaling invariance. In other words, if I introduce a parameter lambda strictly positive, and if I can rescale, if I have a solution of the Einstein vacuum equations, I can cook up another solution of the Einstein equation just by rescaling coordinates by a factor lambda. If G is solution, then G lambda is the again solution of the Einstein vacuum equation. So that's the so-called scaling invariance. And this scaling invariance leave invariant the space. The scaling invariant space here would be H3 half dot. Okay, so here this means that this result is in fact 1/2 above the scaling of the equations, while I should mention that the Christodoulou BV result is in fact at the scaling, and I believe this is very important to go towards the scaling. I'll come back to this. Okay, but still I want to mention that there is some criticality in a different way about this result. The criticality can be seen at the level of trying to control solutions of the equanal equation. In other words, the equation, the scalar functions u that satisfy on your space-time, g alpha beta, d alpha u d beta u is equal to 0. So here, for decontrolling this equation, I claim that it is necessary to have the curvature tensor in L2, and I'll come back to this later. But at this stage, let me just mention for those who are not used to it, the equanal equation is fundamental when you want to build representation formulas for the wave equation, and that's what I did later. So if you want to, use the Kirchhoff formula or the plane wave parametrics formula, or rather their generalization to modular wave equation, this is where you would need to control the equanal equation. So this is really a fundamental object when you want to have any kind of representation formula, and more practically, of course, the level sets of U are just the null points of your spacetime. So it's also a way to control the geometry of your null points. Okay, let me maybe comment a little bit on some recent results, since, as Lars mentioned, this is quite an old result, so let me mention some recent related results. So there has been some extension of this result by some of my former students. So Stefan Schimek has, in fact, extended it to localized results. In other words, our result holds for sigma 0, which has the topology of R3, because we do harmonic analysis. So this is a simpler setting. He localized it in a ball to have this result working only on the domain of dependence of what, right? The domain of dependence of a ball. And then it has also been extended to a different setting than the standard Cauchy surface, to the characteristic Cauchy surface. In other words, when you start with a ball and the cone emanating of the ball. So you set the initial data here, and here. This is the so-called space-like characteristic initial value problem. And this has been extended by Olivier Graft and Stefan Schimek. Okay, so this was for the extensions. Now let me mention two results which point out to the direction of maybe being able to improve this result of the Bondi-Delta curvature theorem, which again I recall leaves 1/2 above the scaling, so it's not critical from that respect. So there is this result of Luke Moskidis, which is not a result on the evolution, it's just a result on the initial slice, but at least it says that if your initial slice is close to Minkowski as measured in the scaling invariant norm, then you don't have trapped surfaces. So that points out to the fact that, okay, at least it's not too bad to work in a scaling invariant space, but of course it's just at the level of initial data. And I want also to mention this result of I, Freeman, Tataru, which prove well-posedness for a different equation, although it's the time-like minimal surface equation in Minkowski. So this is also a quasi-linear wave equation with a null structure. So this is the connection with the Einstein equations. And for this different equation, they can go 1/4 above the scaling, while we have 1/2 above it. Okay, so this raising the question whether you can go beyond the theorem I was mentioning, and I believe that this is actually going all the way to the scaling is really essential for proving the weak cosmic censorship. So I think it's a very important problem. Fortunately, it's a very hard one. Yeah.
So how do you formulate Einstein equations if you don't accept weak data? So that
Well, it's yeah, metric and H3 so that means the Christoffel in H1 you can still make sense of if you think of the curvature as being, of the curvature tensor. So the curvature tensor is of the form, roughly it's like, in a coordinate system it's like this, right? It's GD2G plus DG square. It's still perfectly legitimate because H3 dot, well, or let's say an improvement, let's say that G is in L infinity basically, L infinity is involved. So let's say that you're in the intersection of H3 dot L infinity. So this would be in L infinity and this would be you're right, yeah. Okay, so let me stay with H1 half. So this would be H1 half, this would be, let's say, yeah, okay, I see what you mean. It would be H minus 1/2, so that's okay, yeah, exactly, it works. And here again, the product would work also. So you can make sense, it's borderline, but suppose I give you some buzz-off improvement, some very slight improvement, then you can make sense of these products, yeah. Okay, so it's conceivable that you can go to the scaling, but of course going to the scaling, as you can see, is completely borderline. So this is why it's a hard problem. Okay, so well, no, yeah. So in reality, either you intersect with an NFT or you go to a buzz-off improvement, which gives you a borderline solvability, so that you embed in an infinity. Okay, but in principle, it's not impossible. Okay, let me maybe finish by. Oops, I'm running a bit late. Let me finish by mentioning some ideas of the proof of this result. So I want first to spend one slide on the strategy of the proof. So first of all, I should say this is not, it's a paper, but it's a bit like the result of Crisolo. It's in fact a sequence of papers. There are 5 companion papers, so it's a program to obtain this theorem. And the entire proof can be somehow divided in 4 steps. The first one is to recast the Einstein equations as a quasi-linear Young-Mills theory, and by Young-Mills here I mean classical Young-Mills. So this first step, so remember it can only work because you can find a very fine structure of the nonlinearity, the so-called null structure in the Einstein equations. So here it's about picking a gauge in which you see this beautiful structure. And the way we do it is by analogy with the Young-Mills, classical Young-Mills, which does that. It's a seminar problem which does satisfy the null structure. So here we find a way to find a gauge in which the Einstein equation takes the form of Young-Mills, except of course it is not on a fixed spacetime, but on a spacetime which is the unknown of the problem itself. This is why we call it quasi-linear Young-Mills theory. Okay, so this step is about uncovering this null structure, and then you need to exploit this structure. And the way you exploit this structure is by proving binary estimates. And here the difference with the usual sublinear proofs is that you have to prove binary estimates not on the flat spacetime, but for solutions of the wave equation on a curved background. Okay, and then to prove these binary estimates, the next step is precisely to prove a representation formula for the wave equation. So this is constructing a plane wave representation for solutions of the wave equation on your curved background. And finally, you want to prove sharp L4 Strickard's estimates in addition to the binary estimates, again for solutions of the wave equation on the curved background. So the first step is purely algebraic, how to recast it as a quasi-linear Young-Mills theory. But the 3 other steps are in fact estimates. So this is where you have to work hard to prove all these estimates by only assuming curvature bonds in L2. And this again requires to use the full null structure of the Einstein equations. Okay, let me maybe finish with one aspect of the proof. Sorry, maybe I just want to talk about this construction of the plane wave representation because obviously I don't have the time to mention everything. So let me tell you how you cook up a plane wave, and hopefully I'll have the time to say a few remarks on the Econal equation. So let's see why building a plane wave is connected to the Econal equation. So let me take this as my plane wave. My plane wave is EI lambda U of Tx omega, where T and X, of course, are my space-time variables, and lambda and omega are Fourier variables. In other words, you should see that they correspond to a Fourier variable in R3 written in spherical coordinates. So lambda is the norm, and omega is the direction of my Fourier variable. Okay? And I want this to be a plane wave, which means that I want this to be a solution of the wave equation on my curved background, or rather here it will just be an approximate solution. Okay, so you plug the derivation on ei lambda u, and you obtain, in fact, two terms, one where both derivative falls on the exponential, that would be the first term, and because they both fall on the exponential, you pick a lambda square, or the second derivative falls back on the phase, and then you get the derivation of the phase with just a lambda. Okay, so lambda, remember, it's a frequency, which you should think that this means that these terms cost me two derivatives, because I have a lambda square, and this one only one derivative, because I have a lambda. And it's well known that the wave equation loses a derivative. It's unlike elliptic equations. So this means this is a dangerous term, and you have to kill it. And to kill it, of course, obviously you want to make this to be 0, which is exactly the econal equation, d alpha beta, d alpha u, d beta u is equal to 0. So this is exactly why these representation formulas are always, in some sense or another, connected to solutions of the econal equation. Okay, and if you do this, then you kill this term, and you are left with this equation, which, as you can see, now I don't have a solution, an exact solution, I just have an approximate solution. In fact, it's a well-known procedure to do this. It's the so-called lax parametrics. Just in geometric optics, lax parametrics will give you an approximation at any order. But it turns out that in the lax parametrics, there's only, at the level of regularity we are working, it's only the most basic term that makes sense. All the other terms will not make sense. Okay, so maybe let me tell you what you get in Minkowski. In Minkowski, of course, so Minkowski is very simple. In Minkowski, your solution, your plane waves are simply u, the solutions of the econal equation are just u plus or minus t plus x dot omega. This would be your solutions of the econal equation, which give you plane waves. And of course, in Minkowski, the derivation is the flat derivation. U is a linear function, so this becomes 0, and you can see that in Minkowski you get an exact solution. Okay, but on a curved spacetime, you just get an approximate solution, which fortunately is good enough for what we want to do. Okay, so that's one approximate solution to the wave equation. And of course, if you want to generate any initial data, you now want to superpose your plane waves exactly as in the Minkowski spacetime. Okay, so you're going to take the sum, infinite sum, or in fact an integral on these plane waves, and you're going to get an oscillatory integral in the form of a Fourier integral operator, in the sense of Hermann and Wustermann. Okay, so you want to superpose these plane waves, and again, everything relies on the econal equation. Because you have a Fourier integral operator, you expect to integrate by part to make sense of this oscillatory integral, and because you want to integrate by part, you want to extract as much regularity as possible with respect both to the variable tx and omega. Okay, and of course here, the main difficulty is that you only assume curvature bounds on your spacetime, and again, that will require you to use the full structure of the Einstein equations to be able to control the econal equation. But however, this first point seems to only limit regularity with respect to t and x. It seems a priori that with respect to omega, you would be smooth simply because the omega is just a parameter in u, but the metric has nothing to do with omega. Okay? And it turns out that actually it's a naive idea, simply because this equation, this econal equation, is a nonlinear transport equation. So as any transport equation, it's better, it gets one more derivative in the direction of the transport. But once you differentiate with respect to omega, out of this good derivative, you get a bad derivative, and this induces a loss of derivative. And this is why, in fact, you are also limited with respect to omega. Okay? So you just have to hope that you have enough regularity in the end to perform your integration by parts. And here I should also mention that because it's a nonlinear transport equation, you have to choose the initial data, so you have to choose u at your time 0. So you are transporting, right? You have your initial slice sigma 0, and you are transporting, somehow you are transporting your solutions, u, from the sigma 0, but you have, of course, to make an initial choice. And this initial choice turns out that if you want to extract as much regularity with respect to omega and x as possible, turns out that we came up with only one good choice, which is actually related to the mean curvature flow. In fact, it's the mean curvature flow. It's exactly the mean curvature flow with the right-hand side, which is a contraction of the second frontal form k with suitable directions. Okay, and maybe let me end up with a comment on why I said that curvature in L2 is minimal to control the econal equation. And this, in fact, you can understand it even at the classical way of constructing solutions of the econal equation. So the classical way of constructing solutions of the econal equation is just by using the method of characteristics. And here the characteristics in my problem are just the null geodesics of my space-time. So you want, in other words, the method of characteristics breaks down where you follow U along a characteristic, but unfortunately, this U is constant along each of these characteristics. But of course, if they meet again in the future, then you have a problem on define U. Okay, U is constant along this one and this one, but if they meet, you have a problem. So what you want to avoid is that this characteristic will meet again, and geometrically, this means that you want to get a lower bound on the radius of injectivity of these level surfaces. And it turns out that curvature in L2 is precisely minimal to get this very, somehow the most basic estimate you have to do to start with, which is to get a lower bound on the radius of injectivity. Okay, I'll stop here. Thank you very much.
To know what does the value of curvature conjecture imply for classical lineals on fixed curve space-time? Do you get global existence as long as the lineal's curvature is in L2? And the second question, in that case, would you still need to control the Eigner equation?
Yeah, so the answer is I think the answer, so let's see, the answer is no and no again. So the first equation, no, it doesn't, this is a local in time result for very rough solutions. It doesn't tell you anything on it doesn't tell you anything on long times. So it wouldn't tell you anything on long times. In fact, you should see Yang-Mills is somehow, it's the opposite. We take the proof of rough local existence on Yang-Mills, it's a proof by Klainerman and Macedon from the 90s. They have a proof where they prove local existence in H1 for Yang-Mills. This is exactly the proof we are trying to copy in the quasi-linear case. So what you can do is hope that something in the semi-linear case, you can try to be inspired to make it work in the quasi-linear case. But the quasi-linear is strictly harder. It never goes the other way around. Usually you know how to do something in a semi-linear case and you go to quasi-linear case. Now the second question, sorry, I forgot what. The economic question. Yeah, well, okay. No, so if you want to rely on the representation formula, the problem is that you don't really, for long time existence problem, like the one you mentioned, you usually don't rely on the representation formula. You rather use vector fields but if you wanted to rely on the representation formula, you would just have to use the solution of the econal equation on your fixed background, so it would be much simpler. Right, you would just have to understand the econal equation. I don't know if you think of looking at Yang-Mills on Schwarzschild or Kerr, you just to understand the econal equation on Schwarzschild and Kerr. This is very well understood, of course. So you wouldn't have this kind of problems. Right here the space-time is an unknown of the problem. So this is the difficulty in controlling it. Yeah, no, absolutely not. Yeah. You mean in the result of crystal rule?
The surface.
Yeah.
Is it smooth or any irregularity?
Well, okay, so in the work of crystal rule, he's in spherical symmetry, so it's a round sphere, right? So then it is automatically smooth. Of course, in general, okay, in general, it's a good question. I think in the work of, so there is a work of Hahn that works outside of spherical symmetry, but looks at the instability of the singularity of crystal rule. And I believe that he also gets smooth. In fact, he constructs the smooth apparent horizon for this solution. So I think, yeah, it would be smooth.
I'm curious about why the roughness was really necessary for crystal rule in the following sense. What you described was he took a non-zero but very small energy density outside the gas electron at the center of the But if he added just a tiny little bit of energy inside, so that it would have become smoother, would extra energy inside really have prevented it from forming the pipeline?
No, so you're right.
Maybe the proof is harder, but it's
No. You're perfectly right. So if you want, then he has also an approximation. He can show that this rough data can be approximated by a smooth data, but somehow still the essence of the proof is with this rough data. So if you want, you can. So in other words, after the fact, I can tell you that of course, I have a sequence of smooth data converging to it. So they will also have a trial surface, but as smooth solutions, there will be larger and larger measure in this. There will be small only in this norm. They will be large in the smooth norm and small in this rough norm. But you're right. After the fact, it's actually easier to do the way he does and then approximate by a smooth solution. So we can even produce smooth.
So the proof is but then you learn that the answer was true.
Yeah, exactly.
Okay, maybe one more question. So you mentioned invariance, so it's easy. When you say invariance, you need to look at some other surface. Is it still going to be L2 in the corresponding surface?
Yeah, no, so when I say invariance with respect to coordinate change, so if you, in other words, if you are working, suppose you are working, we work with very specific coordinates in which we see young meals. I claim this is not necessary. If you are in other coordinates, you just have to make sure that the curvature is in L2 locally, and then that means you can extend the solution. So if you choose another surface, you'll have to check that curvature is in L2 in this other surface. But it's an invariant information. In other words, curvature in L2 doesn't require to choose a specific curvature coordinate system.
No, but my question is more like, if you just change the surface, so let's say you have the solution as space, and then you take another surface, another smooth surface, it's going to be in the corresponding surface, in that surface.
Well, if it's yeah, sure. I mean, if it's a sufficiently regular surface, you will be L2 in a slab around that surface. So as long as you are in the slab, where I guarantee every slice, well, every sufficiently regular slice will be in L2, yeah, because you just by, yeah, certainly you can just run. In fact, you can immediately look.
It's not any function that's in L2 some slices are going to be.
Yeah, sure, but you see, it's consistent with just the energy. Think of the wave. If I ask you this question for the wave, it would just be a consequence of the energy estimate. In this result, we are able to prove it because we are able to prove the energy estimate. And then your true is not true for every function, but for a solution of the wave equation, it is true nevertheless. And that's what's important.
In questo duro argument, why if you develop the trapez surface, then the singularity is defined relative?
So you can really he really shows. I mean, there is really he shows that in fact it starts from below the. So he's in spherical symmetry, so it's on the axis. So first of all, the singularity is on the axis, right? The singularity is on the axis, and he really shows. So let's say this is back on. He really shows that in fact there is an apparent horizon forming before going all the way to infinity. I mean that's an apparent horizon. So if you want the trap surface is here, but once the trap surface forms, you can even show behind that there is an apparent horizon, which separates the singularity from null infinity. Right.
Because from infinity you cannot see
Yeah. So in other words, from null infinity, you will not see it. It will be inside the. It will be really the. In fact, the black hole will be here, right? So that would be the boundary of your black hole. Somehow your black hole will be here, right? As soon as you are on one side of the, as long as you are on the wrong side of the apparent horizon, you are hidden, right? Because the black hole, what you see from null infinity is even beyond the apparent horizon. So in Schwarzschild, the apparent horizon and the event horizon are the same, but usually what happens is the apparent horizon is slightly inside the black hole. Okay, so if you put it inside so if you want putting it on one side of the event horizon, it's very difficult to know. But if you have a trap surface, you can be sure you're inside the apparent horizon, and therefore you are strictly inside the black hole.
Okay. Yeah, so this is very enlightening discussion, and also was very important. Really focused on this very important aspect of the rough regularity, rough initial data problem, that it's motivated by the weak topic censorship in general.